So we're going to try to get started. I know this is not playa time. We're actually just a few minutes late, so I apologize for that. So first of all, welcome to Campus Callosum. This is a camp I discovered last year. They're amazing people. It's filled with neuroscientists, smart people like Janis over here and many others. And part of what they give back is a series of lectures on some amazing subjects. This is what happened yesterday, the neuroscience of psychedelics. It's always a popular talk at this camp. And these two boards are from that. We may draw on a little bit of that one. I've summed up our talk on that board by Deb, consciousness and a line going to coma. So ours is going to be a little simpler than this talk, right? But I think you'll find it really good. So let me, I have notes here because normally, as we all do, we give talks with PowerPoint, and with my mind, that keeps me focused. And without a PowerPoint presentation here, at the end, this would be a totally different talk. I'd be off on some other talk. So I'm going to use my notes to try to stay on topic, all right? So consciousness, I think a lot of people understand what that is here. Coma is a disorder of consciousness, right? So I think so. That's the starting definition. Let me just introduce our panelists here. We're going to try to figure out how one of these topics can help us understand the other, and vice versa. So we have Janis. I'm going to let them give their bio when they start talking a little more deeply, but. A lot of consciousness research actually was from Europe. Some of the early people working at, like Freud and all that. So at great expense, we flew in a German neuroscientist here, Janis, in Berlin. He happens to live in San Francisco now, so it was a short flight. So Janis is an expert in consciousness. And then Deb is somebody that I've known for a while now, and she's a neuroscience nurse, a PhD in nursing, and with a lot of expertise in dealing with comatose patients and spinal cord injury patients. And she will do the right side of that really intricate diagram over there. So she'll talk about coma. And then what I'll try to do is I'm working a lot in a new project that we'll talk about. It's called Curing Coma. And we're going to start doing some of the data analysis for that. So can we collect data? Can we come up with models? And can we predict things? Like, can we predict when somebody's coming out of a coma, or how they're going to be and all that, which is a bad problem. And then we have a guest speaker that I just met on the naked bike ride yesterday. I didn't meet him. I've known him for almost 20 years, and he's in the back, and he'll come up here at the end. So his name is Stirling. And when you do data analysis, whether it's coma or whether it's anything, you usually try to collect data, you create a model, and then you run the data through the model and try to see if you can predict things. And what Mark does is he predicts earthquakes and volcanoes. And he's especially relevant to Burning Man in that he did his PhD at University of Nevada in Reno, and part of his thesis was the playa here and all of that. So he knows this area down to the historic level, and he can tell you that. And so he's going to talk about how do you predict an earthquake, and then we're going to try to use that and see, can we use some of those tools to how do we predict coming out of a coma. So we'll try to pack all that in an hour, and we'll see what we get. All right. So the first thing I want to start out is what we're trying to do is solve what you call a big problem. All right. And big problems are things like climate change, right? That's a huge problem, right? Cancer is a big problem, right? And the medical community started, a couple of decades ago to say we're going to really, solve cancer, and they're getting there. They've actually made a lot of progress. In my field and Deb's field, in neurocritical care, that field is actually pretty short. I mean, the profession only started 20 years ago to be a neurointensivist, and so we don't really know a lot about it. And what they did is they got together in 2017 and said, as a profession, what should be our mission, all right? What should be our moonshot, project? And they said, and they decided coma would be it, because a lot of head injury results in coma, and they really know nothing about it. So it's kind of this overarching problem that neurointensivists face, right? And at the meeting, when they announced it to the society, I was in there, and they said, look, we can't solve this as just a profession. We need help from a much wider audience. And they said two things. They said we need community and we need creativity. And I said, where's the best place for community and creativity, right? Burning Man, right? And so I proposed we do a talk at Burning Man, and of course they all laughed, but that's what led to this talk, is bringing a tough problem to some amazingly creative people like you folks and like my panelists here. And we're going to see where we get with this talk by the end. So that's the purpose of this. And I think that's what I need to say. So let's start with Janis, and he's going to give us some basic kind of framework of consciousness and tell us about what he does, and we'll see how that ties in.
Yeah, that sounds good. All right. Hello, everybody. I'm Janis. I'm a neuroscientist at UC Berkeley, and I study consciousness and psychedelics by sticking electrodes into brains and then recording from like thousands of neurons to see like what's the mechanisms of how consciousness works and how psychedelics works, and whether we can use psychedelics as tools to understand consciousness. And so yeah, I can maybe give a basic intro on consciousness. I'm not an expert on coma, but maybe we can first crowdsource like a definition of consciousness. As many of you may know, it's pretty hard to define a concept, but perhaps I can ask all of you to just shout out some words. What are the properties of consciousness? Maybe that way we can kind of nail down what it is together.
Awareness.
Awareness, okay. Actually, let me write all these down on the whiteboard over there. Actually, yes, there's a pen.
That's true.
You know what?
Yeah, awareness is a word that's very similar to consciousness, I believe. In my view, the difference between consciousness and awareness is very subtle, but I think awareness refers more to the part of consciousness that's related to being able to react and like to a stimulus, like process it and then report it, for example. But they are very related. Any more properties of consciousness? Just shout out the first word that comes to your mind. Lucidity. Oh.
Thought.
Sorry? Thought, yeah. Thoughts are an important part of consciousness, at least in humans, right? Well, I don't know, maybe fish think as well. Narrative? Oh, that's good. What else do you think are essential properties of consciousness?
Awake.
Sorry, one more time?
Awake.
Awake?
Awakefulness?
Yes, I think most of the time, yeah, you need to be awake to be conscious. I guess dreams are an exception, where you hardly ever are conscious. I don't even know how to spell that. Can you explain what that means?
To be aware.
To be aware, yeah.
Cognitive.
Cognition, yeah. Now I want to add to that, since we have cognition, I also want to write down perception. Yeah, over there.
Being able to think.
Being able to think. Intention. Intentionality. That's actually very important. People often talk about like qualia and intentionality as the two components of consciousness.
What about attention?
Attention. yeah, often if you see something, to become conscious of it, you have to attend to it. Not always. In some rare cases, you can dissociate those two things. Emotion? Yeah. That's great. We got like cognition, like thoughts. We have perception, like seeing stuff, like the color red, or it feels like to see color red. And then there's also emotions, which are also very important, which is different from perception in some sense. It's like
How about accumulating memory?
accumulating memory.
Yeah.
Mm-hmm. Right. You can, for example, recall the face of your mother, and well, it depends on the person actually, but a lot of people will have a vivid image of the mother in their mind, but probably a couple of people in the audience are aphantasics, which means that they actually are not seeing anything at all. Like when you're trying to visualize something, there's, I think, about 20% of people are not seeing anything.
Janis, I have one, alterable.
Oh, yeah. Well, I think you cheated because you had that thing behind you. Yeah, that's great. Yeah, let's keep it at that. Maybe for my definition of consciousness, I would add two more words. One is private. Yeah, I have a conscious experience, and I cannot really directly share it with you. I can maybe describe it, or draw it, but there's no way for you to have direct access to my consciousness. In fact, there's no way for you to know that I am conscious. Only I can know that. And the second property I would like to add is subjective. Yeah, so what people describe as qualia means the quality of what it feels like to see, for example, the color red, or drink a red wine, or touch the playa dust. And that's different from a physical description of what happens in your brain, you see? Because maybe I can allude quickly to a thought experiment. Let's say there's a physicist called Mary, who is a brilliant physicist. She knows everything there is to know about color, the neuroscience, the physics, everything that is humanly possible to know. But let's say she is colorblind. So she's actually never seen color herself in her life. Now if she gets cured by some miracle cure and sees for the first time, she learns something new. And that new thing she learns is what it feels like to see color. And arguably, that's something she couldn't have learned from all her studies of the physical description of consciousness. And that's because it's first person and private. Should I go a bit about some work I do, or should we move on?
I think how you study it. I mean, maybe give it what you do as an example of how do you study consciousness. I think that's
Great, yeah. Yeah, maybe talk a bit about my research that I do at UC Berkeley. So, as I said, I stick electrodes into brains to record from over 1,000 single neurons, and sometimes I also stimulate parts of the brain and see how that affects other neurons. And we're trying to find out the mechanisms of consciousness. Like, how does your brain generate consciousness? Where does it come from? Is it like a particular region in your brain that generates consciousness, and then maybe if it gets knocked out, you become a philosophical zombie that doesn't have consciousness but maybe behaves normally otherwise? And the way I study it is I use ambiguous stimuli. So I focus on studying it using visual stimuli. And many of you have probably seen the phase-vase illusion. Or if you want, over there we have these red Xenon goggles. If you put them on, you will see a stimulus there where your perception switches. So it's always the same image, but your perception of it switches between one interpretation or another. And in my opinion, that's the best way to distill neural correlates of consciousness, because basically you have the physical input fixed, it's always the same image, but your conscious perception flips from one way to another. And so we're trying to figure out, when your conscious perception switches, when your brain generates a new conscious percept or interpretation of the world, where does it happen first? And how does it happen? So on the mechanistic level of neurons. And maybe I can give you a little bit of very preliminary unpublished results, if you promise you won't scoop me. So far our results suggest that conscious perception, it usually you feel like conscious perception your consciousness is continuous, right? That it happens all the time, and it's fluid. But actually, our research suggests that it's discrete, and that within a given second, your conscious perception actually flips about 10 times between your brain switches between a conscious mode and an unconscious mode. It seems very counterintuitive, and I still find it hard to wrap my head around. But the way it seems to work, possibly, is that your brain has two phases of processing. One is a feed-forward phase. Feed-forward means it's just processing the input. So an image comes through the eye, and then it gets processed and becomes more and more abstract in the brain, going up the hierarchy of the brain. So first you have maybe some very simple neurons that just represent very simple visual stimuli like the color or an edge orientation, and then as you go more to the front of the brain, for example, here in the temporal lobe, you have neurons that we found that are called face cells. So if you show an image, most of the time the neurons won't respond, but if you show an image of a face, then the neurons will fire like a lot. And then in the most anterior brain region, we have even more abstract encoding cells. There are, for example, the so-called Jennifer Aniston cell that will respond and then fire if you see a picture of Jennifer Aniston, or if you read her name, or if you hear her voice. So it really represents the abstract concept of Jennifer Aniston. So that's the feed-forward direction of input processing. But it appears from our results that the brain alternates between this feed-forward mode and a feedback mode. And in the feedback mode, the brain does not process input but interprets the input and actually regenerates the image. So you can imagine like a computer graphics engine that, based on some model of the world, can generate images. And so we believe that the brain does something similar. And it splits it into two phases over time. And it switches very fast between these two modes of processing the input and interpreting it. But you're only conscious during the interpretation. So what you're conscious of is not your brain processing the input, but it is your brain generating reality, basically, based on its model of the world and its own expectations and prior beliefs.
Thanks very much. And let me just try to tie that into some. So if I go back a long time ago when I used to hang out in a neuro ICU, and Deb can verify this. I'm going to introduce her in just a minute. The nurses would tell me that if they were in the room in a comatose patient, that everything, their physiology would be kind of constant. Everything. If a family member came in some comatose patients, and the comatose patient heard, a mother or a family member, heart rate would increase. They would notice these kind of things. So I think that's kind of what you're talking about is that the cognition of something different than the sound. It actually works. So this was years ago. I think we knew this, and it'd be nice to kind of try to tie that into this. So let me let Deb take it over, and I want to ask how many people. So actually, to the right of coma is death. All right. And how many people saw the movie The Princess Bride? All right, it's kind of a cult, all right? And you remember they tortured Wesley. This is a guy who was in love with Buttercup, but this king wanted to marry her and everything. And they tortured him until he was dead, right? And then they took him to this wizard, this guy. And does anyone remember what he said? Exactly, you got it. All right, so there's death and there's almost dead. All right, and so Deb's going to talk about the almost dead. All right, that's kind of maybe a morbid way to say it, but I mean, but the thing is, there really is there's kind of this gray line in there, and so let's let you take it from
Don't stay.
Hey everyone, I'm Deb. Thanks so much for showing up to this. I don't know how I got on this great panel here. I'm not a neuroscientist. I am a neuro outcomes researcher, so I look at quality of life and functional outcomes after traumatic neurologic injury, so brain and spinal injury. And I'm also a 13-year nurse veteran. I work in a trauma ICU, so I have a multifaceted relationship with coma where I research it and I also deal with the patients and the families. And thank you for writing the definition of consciousness. I'll spare you my messy handwriting because it's the converse of consciousness is the definition of coma. So when we think about definition, we're forced into a binary of what is and what isn't. With coma, you're not able to have higher level functions like expressing emotion, creating a narrative, forming memories. But it also is a state of prolonged unconsciousness where you're not able to respond normally to external stimuli like light and sound. You are not able to have normal sleep-wake cycles, and you're not able to be awoken. So who here has been in a coma? I have. Has anyone had surgery? Anesthesia puts you in a medically induced coma. Has anyone taken too much ketamine on the playa and couldn't stand up? Close to coma. So there are gray areas. And when we think about recovery from coma, it often has to do with what got you into the coma. So medically induced coma, anesthesia, very reversible. You're likely hopefully you're gonna return to your normal self after the surgery when they wean down that medication. That would be classified as a diffuse neuronal coma. There's two different classifications. So diffuse neuronal is more like metabolic or toxic in its causes. Metabolic causes could be malnutrition, hypoglycemia, low blood sugar, hypothermia, hyperthermia, if you were here at the burn last year. Your temperature was too high. So those are metabolic causes, usually more reversible than the other class of coma, which is structural causes. So that's when you get admitted with a traumatic brain injury, you have a stroke, you have a massive injury to your brain. And that's when recovery and prognosis gets more variable and often prolonged, and maybe even irreversible. And so medically, how we define coma is through this 50-year-old scale called the Glasgow Coma Scale, which is a 15-point scale. The lowest score you can get is a 3, and that means you are not responding to any stimuli. Highest score is a 15, which all of us have, I hope, where you're fully aware and alert and able to respond appropriately to external stimuli. And a coma is classified as falling in the score range between a 3 and an 8. So even within the scale, we have a scale of how you can be on within your coma. So when we think about family members, the two questions I get are, when a loved one's in the ICU in a coma, the family member will always ask, when will they wake up? And what will they be like when they wake up? And it is very hard to answer that because it very much depends on the reason why they're in the coma. And it also depends on a lot of ethical considerations around what that question means. So when you say, what will they be like, or when will they wake up, I'm really curious about the they and who they are and what's important to them. Because I'm thinking about a patient I had just recently who was at the far end of Dick's beautiful diagram of coma, where it was one hair away from brain death. There's a very complex exam a patient goes through to define when they're actually brain dead. And they failed one of the questions on the questionnaire. So they were just shy of brain death. They were actually able to form some independent breaths on their own without being on a ventilator. So they were technically alive. And we're all thinking, there's not likely for recovery here. They're pretty at the end of the scale. And the family wants to know, when will they wake up? What will they be like when they wake up? And so my question to them is, well, what's important to the patient? You know, what do they care about? And what does alive mean to them? And what's a meaningful life? And the response I got, which surprised me, was they are happy to live as long as they can watch the World Series every year. So the question they asked me was, will they ever be able to open their eyes again? And I think that's probably pretty likely because we have some brainstem function. They're able to form some breaths, so they may be able to eventually, with some recovery, open their eyes. And that was enough for them to continue care. Whereas someone else may say if they can't return to work, that's not a meaningful life to them. If they can't interact with their kids, it's not meaningful. So recovery is very much dependent on the underlying cause of coma and also who the person is that is going to be recovering from it. So I don't know what else you want me to touch on. I'll spare you from drawing diagrams.
So let's, oh, there you go, I got this one. So thank you, that was great. That covered everything I wanted to cover, so you did a good job. So what I want to do now, and we'll get, thank you. So what I want to do now is I want to go back to this, the reason we're here is this Curing Coma Campaign, all right, this 20-year moonshot effort to try to make some progress in this area to answer the questions that Deb brought up. And again, it's a very difficult thing because we don't know a lot about the brain, right? So the things that, so this campaign identified 4 areas initially where they want to work, and I'm going to just go through those real quickly, and then tell you what's going on in there, and then we'll give Mark a chance to talk, and then we'll just open it up to a discussion. So the areas that they thought were problematic, Deb just mentioned the first one, is the way we evaluate a coma is antiquated, all right? And it's this Glasgow Coma Score. And if you think about it, the thing that they noticed is that we're trying to look at consciousness, but the measures of consciousness are all indirect. You look at you actually look at things that require some kind of muscle movement, like eyes, verbal, talking, and motor function. All right, so your muscles. So you're looking basically at the actions of muscles, and you really want to look at consciousness. All right, now it's not exactly that. I mean, if somebody can speak, you know that they're thinking of it. And so, and actually, a couple of years ago, there's a great paper that illustrated what's called cognitive motor dissociation. All right, and so you're thinking, but you can't express it. All right, and so so you can understand things, but there's no way to express it, and that's cognitive motor dissociation. It kind of throws this whole evaluation score out the window, right? Because you may be thinking, and it's yes.
Is that the same as the locked-in syndrome?
I'm sorry, I can't.
Locked-in syndrome, is that what it is?
Well, that's a little different, but because locked in, my understanding. Do you want to answer? Or locked in is I think you can they are arousable just very momentarily. So it's different from that. Locked in syndrome they knew about. This cognitive motor dissociation really was just kind of discovered a couple of years ago. So do you have anything?
Yeah, no, that's a really good question because it's kind of this gray area. She was asking about locked-in syndrome, which we see very rarely, but we do see in strokes usually. And it's where we assume cognition is intact. We don't know how much because it's really impossible to test because they can't have any outward expression of towards stimuli. Usually they maintain some sort of eye movement, so sometimes these patients can respond yes, no with blinking, but other than that, they can't move their body and definitely can't communicate. And so that's kind of a hard thing is we always want to make sure when someone's in a coma that they're not actually locked in. Yeah, it's a rough one.
Yeah, I mean, good point. Yeah. And I think it speaks to the variability in this whole field that we try to overcome. So that's the first one. The next one is there's a very poor prognostic association between when you come into the hospital, how you are, and when you go out of the hospital. And think about this: if you go into a hospital with this kind of made up example, you go into a hospital with a cut, all right, a deep cut or something like that. In the emergency room, they have a real good idea of how you're going to leave the hospital, right? They're going to put antibiotics on it, they're going to sew it up, and you're going to do fine, all right? So they can predict how you're going to do with that cut. I mean, that's an easy one. When you come in with a coma, they'll do all these things. They'll get a CT scan, they'll do all this stuff, and they get all this data. That data and the classification we have rarely predicts the outcome. All right, and would you agree with that? I mean, there's just some classic slides of showing all these CT scans that are very, very, they're very different, but they're all classified the same according to a GCS, and they all have different outcomes. So that the inability to do prognosis from when you come in the door is one of the areas that's a huge problem in coma. Right. The next one is that they are coming out with drugs that are drugs that will try to help you wake up, all right? And consciousness is I guess a seed of that is the reticular activating system, which you know more about than I do. But they have some drugs that try to get that kind of restarted and everything. but the problem there is they're targeting more the symptom, not the mechanism. And the reason they're doing that is because we really don't know a lot of the mechanisms. So that's the other. Then the last problem they saw was that there's this dichotomy between where is head trauma located in the world versus where are the treatments located. It turns out if you're in North America and Europe, that's where about 10% of the traumatic brain injuries occur, but it's where all of the advanced therapies are, right? If you get a TBI in pretty much any city in Europe and in the US, you go right to a place where Deb works, they do an MRI, they take part of your skull off, let the brain expand, give you all these drugs, monitor your ICP, which is what Jana works in right at the front here. And so, so we have the therapies, but 90% of the head injury, I think that's about 90, it could be 80, 90, is in other countries, sub-Saharan Africa, all the rest of the world, where you don't have those treatments. So that was actually one of the things they brought out is how do we take what we learned and make it translatable or into these other countries to really solve the problem. So what they're doing, and I'll kind of wrap this up real quick. They have these 4 committees. The reason I'm mentioning this is any of you who work in the clinical aspects or the consciousness aspects or data science or any of this, there's going to be a lot of money for this. I'm predicting that, even though I'm not very good at forecasting. But they're trying to get like $100 million either from NIH or DoD or something like that. So I think in a couple of years, it's going to be a big pot of money to try to solve these problems. And if any of you are in academics where you need to get grants and you're mildly interested in this, maybe you want to just look up this campaign. So the first thing they want to do is when you study any subjects, particularly one that's the problem's is ages old, and there are people studying it all over the world. The nomenclature tends to get really fuzzy. So somebody calls something this, somebody calls something that. So the first thing they want to do is harmonize the nomenclature. So everybody around the world is going to call this symptom that, right, and nothing else. And so there's this thing called the common data elements that we've been participating in to try to homogenize that. So we're going to create the language for that. The second committee is on mechanism. So it's the kind of thing that Janis does and probably applied more to comatose patients. The third one is on prognostication and see if we can get a feature set of the comatose patient and then project where they're going to be. So trajectories and stuff, and that's what Mark's going to talk a little bit about there. And then the last one is, can we actually, this is probably the most difficult one, is can we reverse coma? All right, so they have a committee there to, can we come up with a drug or something that can actually reverse coma? That would make life a lot easier, for a lot of places. And one of them is the military. That's they're supporting some of our work. Is you're out in the battlefield. If somebody has a hemorrhage or gets shot in the leg or something, they have medics that dive on and put a tourniquet around and all that stuff. And or if they got shot in the lungs, and they can patch that up, and all of that. If you get a hit in the head from a blast or something, you're in a coma, you basically have now a body to deal with out in the battlefield. So it's of high interest to the military. So they're very interested in that, as well as other places like National Institutes of Health and all that. So that's those are the committees, and if you want to learn more about that, it's called curingcoma.org. So what I want to do, I want to switch to just a little bit of the data science part. So what we're doing is, I started a company a couple of years ago to build this cloud-based data system that we're taking data from these monitors that capture all the data, very high resolution data on comatose patients, mostly the physiology. Then we send it to the cloud, we marry it with the medications and future is to the actions that Deb would do at the bedside and all that. And then you harmonize the data. Now we can try to use machine learning techniques to try to figure out what's going on, like prognosis and all this, some of the things, and learn more about the mechanisms of it. So that's what I'm doing. And what I want to do then is, I want Mark to come up here and tell you about how he actually, his business is predicting, earthquakes and volcanoes, and just go through some of the, what are the tools and everything you use, and how you do that. And let's see if we can tie that into coma. And Yes. Oh, yeah. Come up here. Cool.
I just stand beside you.
Yeah, sure. Stand here. Yeah. Sit there with I think we can fit another chair right here.
So I'm Mark Stirling, yonder man from New Zealand, and been coming to this a few years now. 19 times. We've been with Dick many times.
I want Mark to tell you how he found about. I want Mark to tell you about how he discovered Burning Man. You may have already been doing it, but it's
okay. 1994 was doing my PhD in University of Nevada, Reno, in earthquake science, and had a lot of earthquake sciencey type friends who knew all these places. Took me and my late wife Jane out for camping trips. Bit of geology, bit of drinking Sierra Nevada and stuff, and so fell in love with the Black Rock Desert and lots of other places. And my late wife and I came out here for Labor Day weekend for a nice quiet camping trip at the hot springs, and we arrived at Otago hot springs over there, and the first thing we saw was a guy dressed in nothing but mud on a bicycle with wide eyes going past us going, thought, what's this? And we found about 50 of them doing that at the hot springs. Thought, okay, we wanted a quiet weekend, we'll head over to the Black Rock hot springs. There were cowboys there doing shooting practice, playing Garth Brooks full bore. We said we'll go back to the hippies. And we heard about they were all there for Burning Man, and we came out to Burning Man. It was just 2,000 people, and got absolutely hooked from there on. And come and gone, 19 burns later, and I founded Kiwi Burn in New Zealand, which is the first international regional outside of North America. So, and we're having our 20th anniversary next year. So, Dick wanted me to, on our naked bike ride yesterday, as the cocktails went down, the naked pub crawl, we started talking geeky science, and Dick wanted to relate some of the more statistical concepts of earthquake forecasting, understanding earthquakes, to what is done in the medical sciences. And really, you bring it down to fundamental science. A lot of our science is, well, I'm in awe of what you guys do. I don't think of earthquake science as all that complex in terms of what we do. We're doing pattern recognition. We're collecting empirical data sets from our historical record, where you've had instrumental records of earthquakes, written records of earthquakes, and then we extend that back into the prehistoric record by doing earthquake geology. So we go to a fault line, we recognise a fault line in the field. I'm doing a lot of this in Nevada this year. I'm on my sabbatical from New Zealand, and we study those fault lines and work out. We look at the signs, we dig trenches and work out when the past earthquakes have happened. So we accumulate data, and that prehistoric record takes us back into time, and hopefully we can start to see a record of prehistoric earthquakes where the ground's been broken, and we combine that with a historical record. So often we're in a very data poor field, like in Nevada. The fault lines, they go off about every 6,000 to 20,000 years. It's not like the San Andreas fault where it goes off about every 300 years. And in New Zealand we've got the Alpine fault, which is on the boundary of the Pacific plate and the Australian plate, and there we've got a record of 22 earthquakes going back 8,000 years. So when you've got a record like that, you can start to do some pattern recognition, and you can see that the Alpine fault has gone off every 300 to 320 years. Last earthquake was 1717, so we're at about 305 or 306 years and counting. So when you've got good data like that, you can use the average long-term occurrence of earthquakes, and you can use where you are since the last earthquake to do probability models. Most of the time we just say, okay, you've got a 1 in 300 chance annual probability of an earthquake. Whereas with the Alpine fault, you can say, well, based on that history, there's that 20-year range of uncertainty. So we can say we've got an X% chance, plus or minus, of an earthquake in, say, the next 50 years. And that number for the Alpine Fault now is 75% chance in the next 50 years. So we can't predict. Prediction is saying it's going to happen on the 14th of June, 10:30 in the morning, underneath Gurlak, and it's going to be 7.5. You can't do that. We don't have things down like that. Nature is too variable and it's not well enough understood. And weather forecasters can't predict weather, and they have a lot more data than us. But we can do quite reasonable forecasting for big data sets like the Alpine Fault and the San Andreas Fault. And so, but when what we have to do, we have the data, and then we do our best to sort of look at that pattern and see whether there are probability models which match the data. And there's lots of different names like Weibull distribution, log normal distribution, inverse Gaussian. What seems to work best is a model where you have earthquake happens here, and you sort of roughly expect another one in X years' time. The probability model goes up as the fault, it's released in the last earthquake, and it's building up again. And so the probability is rising that you're going to get an earthquake in any one day. But then nature comes in, and you never get to 100% probability of the next earthquake. It's never certainty, because nature is variable. And we have this sort of thing called aleatory variability, which is randomness. And I think, in the coma type space, you've got lots of uncertainty, even though you've got a fair bit of data. But the uncertainty of what sort of level of coma, I mean, I'm speaking hugely out of my field, but just in terms of it being relatively, it's data driven, and it is quite, there's a lot of it. You can't say for certain when you're going to come out of that coma. And I can't say for certain exactly when the southern San Andreas Fault is going to rupture, but it has quite a high probability. So and that nature thing is just like the weather coming, a storm coming 6 hours later than forecasted, or Hillary not being a Category 5 hurricane. It was somewhat less than that, and that was totally at odds with the forecast. So I mean, and unfortunately with earthquakes you slow down the timescale by hundreds of times from weather, and we could be fine for the next 100 years in the southern San Andreas Fault, or it could happen tomorrow 4:20. And volcanic hazard, I sort of work peripherally in that area, and it's a similar sort of thing. You have the build-up, you have a process that has some time dependence to it. You have to have a build-up, you have an eruption, you have lots of effects, then you have quiescence. And it can be very complex. You can have clusters of events. And going back to the faults in the basin and range, you don't have that one earthquake quietness. You tend to have clustered events where it sits around very quietly, and then you have quite a number of events. The area gets active. There's an area called the Central Nevada Seismic Belt, which has had 100 years of major earthquakes. But then you dig trenches on the faults, and you see that the last time those faults ruptured was many, many thousands of years ago. So we try our best with the funding we have available, and maybe one day we'll get to prediction, but it'll take some breakthrough of the kinds that have happened 50, 60, 70 years ago to find a process that we can measure, understand, and then measure on a fault that indicates that very start of a rupture starting to happen, that we could actually say, okay, that's going to go off very soon. Let's batten down the hatches. Yeah. So leave it there.
Oh, that's great. Thanks, Mark. Very good. And so let me just pick up on one thing that Mark said. I was giving a talk at some meeting I was invited to in Lake Como in Italy, and I was following this neurosurgeon, and my talks are always on monitoring and all that. And he said something to me that was pretty telling. So he's a neurosurgeon at a major hospital in Boston, and he says when a head trauma patient comes in, I can manage what I can measure, and then I have to let Mother Nature do the rest. And that's where we are with coma. So the goal is to see if we can measure more, all right? And that's what Mark was saying, all right? If we can measure more about, the whatever the big words you used, all right? The plate tectonics or whatever. If we can measure more of that, we can predict more, right? And so that's kind of where I work, and that's where a lot of the problems are. And Deb, I don't know, do you want to speak to the variability is our enemy as well? And so why don't you speak to that a little bit, and then Janis, I want to hear what you would.
Well, I was actually going to pose a question to Mark, the data scientist, and I'm going to put you on the spot here, because as a quality of life researcher, there's this inherent focus on the outlier. I'm really drawn to looking at an outlier, an anomaly. I'm like, why did this one person totally return to normal after this coma when we did not think they would? And I just, it's like I want to dig into that one person, but you only ever get that one person every so often. And I'm shooting myself in the foot as a nurse, because as a nurse, I would love to be able to tell a family member, 20% chance of recovery, you do the work. I would love to give a blanketed percentage of recovery, but it's just never that easy. So I'm curious, in your fancy predictive modeling, these complex quantitative models that you use, do you ever consider the outlier, and in what way do you do so?
Yeah, good question. We try to, in our empirical data sets, we try to understand the behaviour as fully as possible, but we are always, as scientists, we're all pretty humble. We always think, okay, well, there are some very bold scientists who they will say, I have the answers to everything. They imply that, but they're quite rare these days. Most of us are quite humble and think we're better than scratching the surface, but we still probably haven't seen the worst case event or the best case event. And so in our modelling, we will so like in the case of a fault line like the San Andreas fault, we will look at a worst case scenario of where the whole San Andreas ruptures all the way from the Salton Sea, El Centro area, all the way up to Point Arena, north of San Francisco. And that would be around a magnitude 8.2 type earthquake. And then we look even further, and this is all done by physical modelling, where we're going beyond what we see in the empirical data sets to saying, okay, earthquake physics, if you have this amount of slip on a fault, you're imposing this amount of stresses and strains on the neighbouring faults or on the sections of the San Andreas. And so theoretically, you could set these other faults off and have a linked earthquake. And that's how our earthquake hazard modelling works nowadays. We're going beyond the empirical to look at the extremes, and then we'll do some we call it plausibility modelling, but making sense of it. Does this really make sense? Could this earthquake just go on and on like this? And so that's the process. It's putting human intelligence and knowledge of the physics of the earthquake process into play to make sense of it.
No, you just made me think of too how an earthquake is going to happen if it happens, whereas when we're talking about patients in coma and recovery, there's also those patients who their families decided to not continue care, and you wonder if they would have. And so there's that whole subset of data where you wonder, do we miss out on extra data? Would they have recovered? And we just don't know. Yeah. And
we're involved in a project with anoxic coma. So if you have a cardiac arrest, your heart stops, and if you are one of the lucky ones that make it to a hospital, you're usually in a coma. And there's a study going on right now to try to figure out, these are pretty serious brain injuries because your whole brain's been anoxic, but it turns out a number of those probably would have lived that they pulled the plug on. So it's a big ethical issue, as you mentioned right now. So Janis.
Yeah, so we got a nurse, an earthquake scientist, a conscious researcher, Dick, and our lovely audience. So I would suggest maybe we can try to brainstorm together, see if we can maybe find some new approaches coming up with all these fields coming together to find solutions to either diagnose coma, figure out whether it will be permanent or ways to cure coma. And maybe to give a little bit of a framework, I could talk about the problem of that is like, how do you measure consciousness, basically, right? Or degrees of consciousness, or lack of consciousness, and how does it relate to the brain? I suppose the brain is maybe the best way to measure that or try to solve it. So I was at this conference last month on consciousness, and there was this 25-year-old bet that was done between probably the two most prominent figures in the field, one being a neuroscientist and one being a philosopher. So the neuroscientist and the philosopher, they walked into a bar and in Bremen, which is my hometown, and they made a bet because they were pretty wasted, and the bet was whether in 25 years from then, which is now, consciousness will be solved. I guess that was an example of a less humble scientist, because the neuroscientist was pretty certain that we would have it all figured out, but the philosopher thought it was like a hard problem. Well, that's actually what he's famous for calling it the hard problem. And yeah, so there was an evening at the event where they resolved the bet, and they basically pitted. There's several major theories of consciousness in the field right now, and they were pitted against each other at that event. The neuroscientists lost the bet, so since it's still inconclusive, we haven't figured out consciousness. Big surprise. But maybe I can talk to you a bit about those theories. So the question is, how do you measure consciousness? And one theory is called integrated information theory, which was proposed by Giulio Tononi, and has risen to prominence, and it's one of the major theories. And they say that you can basically measure consciousness. You can have a consciousness-o-meter, and there's just a single number that you can apply to any person or system or rock, and that number is called phi, or integrated information. And basically, the higher this number, the more consciousness it has. And he actually has like a mathematical definition for this number. So for any system, you can compute it or calculate it. And the way, it is integrated information. So it needs to be high amounts of information, but just high amounts of information is not enough, right? Because if you have like a hard disk in your computer, you may have 4 terabytes of information, which might be more than the information in your brain. But that's not enough to be conscious, but this information also needs to be integrated. And what that means is that, for example, in your brain, the memory of the face of your grandma is intricately linked with the smell of, let's say, the pancakes that she made. Whereas on the computer, those photos and perhaps this recorded smell file would be completely separate locations and not interacting with each other. So the information need to depend on each other in a causal way. And actually, based on that theory, they developed a method which computes a heuristic of this integrated information to determine whether a brain of like a patient, whether he might be locked in or actually vegetative, for example. And it works pretty well. And the way it works is basically they zap your brain, like they stimulate it, and then after it gets zapped, they measure the activity of the brain and then compute the complexity of that signal. Yeah? So if you're dead, then if I electrically stimulate your brain, not much is going to happen, right? But if you're conscious, then this will cause a very complex, high entropy sequence of activity. And so that's one way people have been measuring, and that has been very helpful for patients. Do you guys use that actually, Deb?
Not yet.
No, not yet, okay. So yeah, that's pretty new and common, I guess. The other major theory of consciousness that was pitted against this theory is called global neural workspace. And this theory says that what consciousness is that somewhere in your brain you have this global neural workspace. You can think of it as like the RAM in your computer. Yeah? And so if you have an input coming in, like an image, it will get processed and stuff, right? But you will only become conscious of it if it enters this global neural workspace. And this global workspace is highly connected to every other region. And you can think of it like the BMIR, so it broadcasts that information to all the other regions. And then that's how you become conscious of it. So there needs to be this ignition. So it's possible that maybe in coma, if you can repair the RAM or exchange it, maybe they could become conscious again. What do you think? And I would also like to open it to the audience if any of you guys have suggestions, like why don't you guys try this or that?
I just one quick response to that is in my prior career I was involved in anesthesia monitoring. So monitoring the brain when you're going under anesthesia, and there was a company that made an anesthesia monitor that was based on entropy. So basically your brain waves are very random. When you get anesthesia, they get less and less random, all right? And they just measured that, and it was a pretty good predictor of how deep you were in anesthesia. So I think that's a very promising technique. So why don't you, if you have comments, and then let's open it up to you. There's no other lecture following this, so if you want to ask questions, that would be great. So,
yes, here's one idea in relation to that. So, yeah, you can measure, I guess, the complexity of brain signals under anesthesia. And maybe there could be a way also to measure coma. Basically, I don't know if you guys are already doing that, but if you measure, if you have the comatose patient and you measure the complexity of his brain signals while being, well, not awake, but not anesthetized, and compare, and then put him anesthesia and also measure the complexity of the brain signals. If he's in a deep coma, perhaps anesthetizing doesn't make much of a difference because he's already unconscious. But maybe if there's hope, then adding the anesthesia will make a bigger difference in the complexity of the brain signals. Do you think that will make sense?
Yeah, I think that makes a lot of sense. I think it'll be interesting to see what is applicable in the clinical setting. Do you think of someone in the ICU with an injured brain, and do we want to put electrodes on it, and what the risk is there? But I think there's a great potential for it, and especially with your thought about like decreasing the need for anesthesia and the adverse outcomes that go along with that. If they're already unconscious, maybe they don't need it. Yeah, I think that with brain stem function, it gets tricky because you can see someone who's in a coma. So Dick gave the example of you walk in the room with your loved one and their heart rate goes up, and that is something I see, but it's I've never seen it tied to a family member. It's tied to someone walking in the room, and so you think like, some sort of brainstem functions going on where they're recognizing a stimulus in the room and they're having maybe some sort of lower level anxiety response or something, and their heart rate goes up. But that is enough for the family member to say they know I'm here, and they can get a little tricky with the discussion there. Yeah, potential.
So why don't we open it up to questions, and if you have any, we'll be here for a while. And go ahead. Yes.
Discuss more about like the advantage of the coma reaction. The same way like bleeding is a reaction to injury, or like an earthquake is a reaction to tension that's building up in the fault line. Like coma, I think, I don't know, it's a reaction, but there's some advantage to like your body going into that state. Is that the case?
I'm gonna try, but it's a little out of my. I feel like you may be better answering this, but I do. I'll tell you what I do know. There's the two different types of umbrellas of coma. There's structural related coma, which is you've had a brain injury, trauma to your head, or a stroke, which is injury by way of impeding blood flow or too much blood flow if you have a vessel that popped. And so that, I think, is just a disruption in the circuitry because you have added pressure to your brain. Would you say that's right? Swelling creates the cascade that impinges neuronal activity. And then there's the other the other umbrella of coma, which is diffuse neuronal, which I feel like you may be able to speak more on, but that's more metabolic causes. And the treatment for that is just reversing the underlying cause. So if you have low blood sugar, just take some sugar. But I don't know down to the structural level.
Is that okay for an answer?
I think it's one of the big questions that we don't.
Yeah, it's.
If it was that easy.
It's like that was like the pre-question to like if you understand the advantage of the coma, you like measure which variables like affect the predictor later. The same way like to predict an earthquake, you would look at tension on the earth. So like the connection between what advantage mechanically it has with like what it can solve for and get out of later. I don't know if that makes sense.
I think it's hard to do it. I don't think there's going to be one number. I think the brain is too complicated. It's going to be a complex, a multi-dimensional thing that we have to come up with for coma. But I don't know if that helps. Any other questions? Yeah.
I wonder what you think about consciousness in coma in other species. To what extent can we use other animal models in studying human coma consciousness?
Do you know, are there like a lot of animal studies where they induce coma in animals? Is that like a common thing that people do?
I don't know animal research, so I only know human subjects.
In head injury, it's more looking at. It doesn't deal with consciousness, so you take that out of the equation. What they're looking for are things like the release of biomarkers. So if you have a head injury, there's a very complicated sequence of biomarkers that are released. Some are released immediately, some over hours, some actually over weeks and months. And so it's this dynamic nature of just more looking at the phenotype of head injury. It's what can we observe, right? And that's kind of where we are with the animal models. I don't think consciousness enters into the animal models at all, because I think it's probably, well, you can use animal models to study that, but I don't know of any for things like head injury or stroke.
I do think it would be, if it's not already being done, it would be a great idea to try it in animal models where you can have all the tools to study what exactly is happening in the brain to induce some kind of coma, and then with all those tools that you have available in the animal, it might be more easy to cure it, and then you may be able to see what to look for or what tools to develop for the human, which work for coma. I think that's a great suggestion. I'm not sure if it's being done already.
So vets don't talk about comas.
So you had talked about the coma scale went from 3 to 8, but then a fully conscious person is 15. I'm curious, what are the ones like between 9 and 14? What are those experiences like? And that tells us like if it's what those things are.
I would just look around at your campmates and.
I mean, like drunk, like 13. Like I'm curious, like.
Yes, yeah, absolutely. A drunk person can be a 13. So there's 3 subscales within it. There's eye function, verbal, and then motor. Yeah, and so. And the eyes are scaled from 1 to 4, verbal's 1 to 5, motor's 1 to 6. So essentially a 9, so just above a coma. If a coma's 3 to 8. A 9 could be someone who's able to open their eyes spontaneously, so to not any sort of verbal or touch stimulation. Their eyes are open spontaneously, but they can't talk and they can't follow commands. That would actually not be a coma. So yeah. That's called a GCS 9.
No, so they do have other things like
Not the best skill.
obtunded is one definition for in that range of 9 to 15 if you're down there, and then I guess there's one minimally vegetative state is they're working out the definitions for those, but coma is the one where unresponsive and unarousable.
I've got a question. A very high-profile coma case was Otto Warnbeer who was held captive in North Korea for a year because he stole a poster in a hotel in a floor that he wasn't allowed to go to. And the North Koreans released him after a year in a state of coma, and he was brought back to the US. Do you guys know about that case, and what would that level of coma have been? He was breathing, he was minimally responsive, and what would the North Koreans have done to get him in that state?
Deb and I were talking earlier, there's that song 50 Ways to Leave Your Lover. Those of you who are a little older know that song. Well, there's like 50 ways to go into a coma, so it's hard to, it's hard to tell what that, what that was for. Any other questions? Yes?
More on the conscious scale, but about the Janis' mention about the switching between feedback and feed forward. Is there any variance between people or even over time within one person? Is there any variance over time or between people with how much we switch between those two systems?
Oh, that's a great question. Yeah, I think I should study that. Also, within a person in different states, right? Like on psychedelics, which I talked about yesterday, the probably most prominent theory of how psychedelics work is that they basically alter the balance between feed-forward and feedback processing. The hypothesis suggests that it's more feed-forward and less feedback, so you're less biased by your priors and expectations and beliefs. And so it would be interesting to look at, for example, which actually I can do. I just collected the data for that last week, so I should analyze that, to see whether psychedelics perhaps change the relative duration of these phases. Maybe have longer feed-forward phases and shorter feedback phases or something like that.
So be very curious to see if that's like changes as you age, like it does have more feed-forward than feedback, right?
Yeah. Oh, yeah, probably, right?
Argue that maybe feedback is the consciousness.
Yes.
So are we less conscious technically when we're on psychedelics?
Okay, well, so on psychedelics, yeah, the first question, remind me about the psychedelics. Yeah, they have like this critical window, right? And they learn much faster. Most people think, I guess, they're less conscious, but like, yeah, some people think that small babies are not conscious at all. But then again, since it's so open to all the input and so in the moment, maybe it's actually more conscious. I'm not sure how to answer that. But yes, there was some question. What was the question on psychedelics again?
It's a similar thing. Like, are we technically less conscious?
Ah, yes, less conscious. Are we less conscious or more conscious? Well, people say they're in a higher state of consciousness, and there's actually something to it. So this integrated information measure that I talked about, people have been doing like EEG on psychedelics and without, and then they compute something called a complexity index. Basically, how complex is your brain, how predictable it is, or how chaotic is it. And if you look at anesthesia and compared to awake, during anesthesia, this complexity is much lower than during awake. And then when you look at the psychedelic state, it is actually higher than awake, this complexity. So in that sense, they may be more conscious, if you want to call it that.
Kind of already is a way to medically induce higher, like more consciousness, kind of in your field that might probably isn't applicable to patients. I don't want to use any psychedelics, but is there kind of an overlap?
Sorry, can you repeat the part?
It sounds like there's already some overlap between the two worlds now, where you are technically medically inducing more consciousness by that definition of it, which is also what you're trying to do with consciousness.
Yeah, has anyone tried giving psychedelics to coma patients? Okay. Go ahead, Dick, it's your turn. It's on you.
Well, maybe we'll try that and report next year. Let's do that. That's interesting. We were talking about that last night. I think Are there any other questions? If not, I would like to thank my esteemed panel, all of good friends of mine, and thank you very much, and really appreciate your contributions. And thank you all for coming to this. We'll be around if you want to ask any other questions, or if you want to find out what playa dust is made of. Mark can tell you about that. So thank you very much. Appreciate it.